We have learned so far about different hardware modalities, how they may affect our functional model, and the hardware-aware synthesis feature. Whether it's classical or quantum, code is meant to be executed. Let's learn how to do it with the Classiq platform. We'll start with a very simple circuit, so we can analyze the results properly. Let's create a state preparation of 2 qubits for the probabilities 0.1, 0.2, 0.3, and 0.4. We can do that by choosing the state preparation Q mode and edit the probabilities. That's our circuit. Now we can click the execute button. Welcome to the execution screen. From here, we can control our execution preferences, perform multiple executions at once, and compare our circuit's performance on multiple hardware. But let's do it one step at a time. The left side of the screen allows us to choose the backends, filter by the different providers and the backend type, whether it's a hardware or a simulator, in order to find your favorite machine. Most of the backends require credentials that you may get by opening accounts on the respective provider, such as IBM Quantum, Azure Quantum, Amazon Braket, and IonQ. We will start by using the Air simulator, which runs inside the Classiq platform, meaning you don't need any firmware credentials. The right side of the screen allows us to modify the execution preferences. For now, we will focus on 2 preferences, the number of shots, which we will keep, and the transpilation option. It allows us to transpile the circuit before execution to better fit to the backend, with different levels of optimization. We will keep it at the decomposed level as well. Now we are ready, let's run! We are redirected to the job screen that represents all the execution jobs we have submitted. We can see that the execution result is indeed what we anticipated, a rise in amplitude of the states 00, 01, 10, and 11. This was a simple exercise, making sure we know what are our options. Let's see what else we can do with a bit more sophisticated example. Back to the synthesis table. Let's scroll all the way down to the Q mode called Learn Functional Level Design Arithmetics. Adjust the max width to 7 and synthesize. This circuit prepares a couple of registers in different bell states, 00 plus 11 and 01 plus 10, and afterward adds them up. The interesting part of the circuit is the adder, since it behaves differently at different connected hardware. And we can even see that before executing the circuit. We are going to execute the circuit on 3 different backends, from 3 different providers. Let's choose IBM Nairobi, Amazon Braket SV1, and Azure IonQ QPU. By selecting all of them, we execute the circuit on them simultaneously. We can also press the Compare Hardware button, which transpiles the circuit to the hardware that we chose. It allows us to look at the differences between how different hardware will digest our circuit. In our case, we can notice how the trapped ion hardware of IonQ will result in a shallower circuit for us than the superconductor computer of IBM. You can even compare the backends by a very simple yet important feature, the waiting time, by clicking the arrow next to the backend name. For this example, I'm going to choose the IBM Chasm simulator and IBM Nairobi. We are ready to execute just as a new screen pops up, the credential screen. Since we chose backends that run on a cloud, or different clouds for that matter, we need access to use them. But don't be frightened. If you don't know how to get these credentials, click the Need Help button for each provider to receive more information. These credentials may also be saved on password managers for easy integration with the ID. Clicking Run will create 2 different jobs, one for each backend. Let's go back to the most basic question. What do we really execute? We execute a classical algorithm, a hybrid algorithm to be precise. Every quantum algorithm that you can think of is actually a classical algorithm. The simplest one being take this quantum circuit, sample it 1,000 times, and return the resulting histogram. A bit more hybrid than that is Grover's algorithm, where we sample the circuit, verify classically the results, and maybe sample again, a different circuit this time. The list goes on, and so we need a way to describe what is going to be executed when we press the button. This all leads to the classical functions, being part of the model itself. Each model contains a classical main function that describes the algorithm. Its functionality will be expanded as we grow, and you will be able to describe more algorithms with it. Learn more about our classical functions in our documentation at docs.classiq.io. I hope you enjoyed hardware lessons and learned how to integrate the hardware into each step of the Classiq platform.